Hi. Now we would like to analyze a circuit in frequency domain. We have two objectives while we are doing this. One of them is to think about it, how we can solve the question. The question says, in this circuit, calculate that VC. So that means capacitor. In frequency domain, it's going to be the phasor, so VC. So that is VC. We are going to calculate now. So in order to calculate VC, it doesn't say that find out all the elements current and voltages. It says calculate VC. So only one element we've got here. One element voltage phasor to be calculated. So our aim to write minimum number of equation. The best case is one equation, one number, isn't it? So we are going to think how to find that equation. That's the first objective. The second objective, what we have done here, after the calculation, we are going to find the phasor. That's a complex number. From that phasor, I'm going to find the corresponding sinusoidal function in time domain. So how we are going to check that our phasor calculation was correct or not? So the way to checking is use the simulation. So we've got Proteus as a simulation tool. So we're going to use this tool and check our solution. Proteus give us the time domain solution. So we are going to correspond those two sinusoidal functions. So this is going to be a separate video. Not within this video, it's going to be a separate one. So you could see it anyway. Now, so two objectives. Let's start from the first one. So we are going to calculate VC. So the current reference we choose for the capacitor should be according to passive sign convention. So it's going to be downwards because the capacitor voltage reference is given. So current reference is downwards. While I'm choosing the inductor current reference, I'm going to choose it as upwards. I'll explain you why. Because this current here is voltage controlled dependent current source. This dependent current source current is controlled by this voltage. This voltage is the capacitor voltage. So this voltage is capacitor voltage. Since this dependent current source is connected to that inductor in serial, that current is going to be this inductor current as well. So I can write this inductor current in terms of VC, which is my unknown. And I can write this capacitor current in terms of VC by using the definition relation. So I'm going to choose the resistor current reference that way. And I'm going to write this current in terms of VC. I will explain it later on. So if you consider this node KCL, Kirchhoff current law equation. So it's going to be this current, which is capacitor current. The sign is positive because it is coming out of the node. So this is towards the node. This current is towards the node, and that is minus IL. And this current is coming out of the node, so plus A R is equal to 0. So I am saying I can write this current in terms of the VC. I can write this current in terms of VC. I can also write that IR in terms of VC. How? This IR current, this resistor has got two terminals. This terminal node voltage is VC. The other terminal node voltage is VS. So VC minus VS over 20 is going to give me this current. So that means I can write this current in terms of VC. So what I'm going to write all this, we need the impedances. In omega domain, the impedance of a capacitor is 1 over C omega C, 1 over C. Omega is this now. That's the natural frequency. So it is 10 to the power 4. C is 10 times 10 microfarad, that means 10 times 10 to the power minus 6 is equal 4, 5 minus 6 minus 1. If I move it to upwards, so it is 10 over J. This is the impedance. So if we consider the capacitor definition relation, VC is equal impedance IC. If you are going to write the IC in terms of VC, so this is going to be IC is equal J omega C VC. So this is 1 omega J. So J omega C from this. That means inverse of this is equal J over 10. So this is admittance. This is impedance. So for the inductor, impedance is J omega L, J omega 10 to the power 4, and L is 4 millihenry, 4 10 to the power minus 3. So that's going to be 40J. What about Vs? Vs as a phasor is going to be 10 e to the power J independent source angle, that is, let's say, Vs. So this angle is 0, so that's going to be 0, that's going to be 1, so that is the phasor. Now let's use this information in here to transfer this Kirchhoff current law equation, unknown Vc, only one unknown Vc included, and Vs as independent source known included. So for IC, I am going to write admittance multiplied by Vc's name. So admittance J over 10 multiplied Vc minus IL, inductor current. I said this current is the same as this current, so this current is 0.1 Vc, so the 1 over 10 Vc plus IR, this resistor current is, that is Vc, that's terminal node voltage is Vc, Vc minus, this is Vs, node voltage, over 20, gives me this current. So this is this current, this is this current, and that is this current, equal to 0. So if you look at this equation now, we've got Vc as an unknown, Vs is known, one equation, one unknown. So if you put it in one Vc parenthesis, J over 10 minus 1 over 10 plus 1 over 20 Vc is equal, this is minus Vs over 20 on the right hand side, Vs 20. If you multiply both sides by 20, it's going to be 2J, and 20, that's minus 2, that is 1, so minus 1 Vc is equal Vs. So Vc is equal 1 over minus 1 plus 2J Vs. So if you move that complex number upwards, that means to the numerator, so we're going to multiply this by the complete conjugate of this number. So let's do it. Okay, we'll do it in VC. Minus 1 minus 20j, 2j over minus 1 plus 2j multiplied complex conjugate of this minus 1 minus 2j Vs. So this is square of the real part, square of the imaginary part, add them up, square root of it. So it's going to be not the square root, so the summation of the squares. So it's going to be minus 1 minus 2j. Square of this 1, square of this 4, add them up, 5. Multiplied Vs, which is 10. So then my Vc is equal 1 over 2 minus 1 minus 2j. Now this is a complex number, and this is the phasor of my capacitor voltage. So if I want to transfer this phasor to time domain, it's going to be a cosine function like this independent source function. So for that reason, for that transformation, I need to transfer this phasor to polar coordinates. So that is 1 over 2. Module of that is the square of the real part plus the square of the imaginary part. Sum them up, square root of the result. So it's going to be square root of 5. That is the module of this complex number. Now to come to angle, so this is in the third quadrate, isn't it? So that means what I'm saying here. So that is imaginary, that is the real part. So real is on this side, imaginary is on this side. So my complex number is in here, third quadrant, 1, 2, third. So that means if I calculate e to the power j arc tangent to this over this, so I'm going to find the angle here. Either I'm going to add pi 180 degree in order to find the phasor here, or I can subtract whatever I found here from 180. So what I said, I will be doing it here. So that is, this number is in the range of 447. So this angle gives you 63 degree. 63 degree in here, isn't it? So because I consider this is positive and this is positive, so in this quadrant it is 63 degree. 63. On this quadrant, pi 180 minus 63 is going to give me that angle, isn't it? So 180 minus 63 is going to be, so that's 117, a to the power minus j 117. So that is my phasor. If I write the corresponding cosine function for this phasor, it's going to be VCT is equal 4.47 cosine. So this part is going to be the same because we know the angular frequency, source, independent source angular frequency is going to be the same for all the elements, current and voltages. So 10,000 omega plus minus 117 degree. So this is not omega, of course, that is T, isn't it? Omega is this. T. So this is my sinusoidal function. This is what is asked. Now, this solution is the particular solution. We know that. In frequency domain, we will find a particular solution. But if you are using the simulation technique, Proteus, so it's going to be general solution that we are going to find. General solution is equal homogeneous solution plus particular. So in frequency domain, in this domain, we cannot find this. Let me make it different color. We are not going to find this. So what we found here is this one. That is particular solution. That's my particular solution. Okay. What we said at the beginning was this. We said if this circuit is stable, that homogeneous solution is going to be zero in a short time. We are going to observe the particular solution only as a general solution. So under the assumption that homogeneous solution is equal to zero, that means the circuit is stable. So we are going to see in the Proteus simulation that we are not going to observe. We won't be able to observe the particular solution. The reason is this, because this circuit is unstable. In frequency domain, we all know, we already know that there are some constraints. In frequency domain, I cannot say whether the circuit is stable or not. I cannot say. That means I don't know the stability of it. If you don't know the stability of it, then there is a risk, isn't it? Particular solution may not be equal to general solution if the circuit is unstable. So this is specifically unstable. So we are not going to observe this particular solution in the Proteus simulation. But still we are going to do this simulation. We will see that homogeneous solution is dominant solution when you compare it to particular solution, because this is going to go very high values in a short time. So that is our expectation from the Proteus simulation. So the second objective, we already said that, find our calculation, check whether it is true or not. So in this case, what we are going to do is this. We are going to make this circuit stable by changing this parameter. After we make this change the parameter, make it stable, I'm going to find the particular solution for that stable circuit, and then for that stable circuit I'm going to compare my particular solution as calculation and the simulation result particular solution, and check those two. At the same time, check whether our calculation is true or not. So let's close at the moment.